Deflection in beams, the double integration method. In this lecture, we are going to examine a mathematical basis for calculating deflection in beams. By the end of the lecture, given a beam, you would know how to formulate an algebraic equation for representing its deflection. Here is a beam, and here is its elastic curve. Let's refer to the beam's deflection as v. Note that v varies with x. V is 0 at the beam's ends, but it changes value in between the ends. We wish to come up with an algebraic equation that enables us to calculate v at an arbitrary point x. To get our equation, we start by drawing a tangent line to the elastic curve at an arbitrary point. Let's denote the angle that the tangent line makes with the x-axis by theta. That is, tangent theta is the change in deflection, dv, with respect to change in x, dx. Let's make a simplification here. Since a beam's deflection is relatively small compared to the beam's length, then theta is a relatively small angle. Therefore, we can equate tangent of theta to the angle itself. That is, if theta is given in radians, we can write theta equals tangent theta. But is this a reasonable approximation? Let's put it to the test. Say theta is 10 degrees. In radians, this is equal to pi over 18, or 0.175. Tangent of 10 degrees is 0.176. As you can see, the two numbers are almost identical. So this simplification is okay. We can write theta equals tangent theta equals dv dx, or dv equals theta times dx. Integrating both sides of this equation, we get v equals integral of theta dx. Now, to actually come up with an algebraic equation for v, we need to integrate the right-hand side of the equation. To do so, we need to represent theta in terms of x. But how? This can be done by expressing theta in terms of bending moment in the beam. And since we know how to express bending moment in terms of x, then we can easily calculate the integral of theta dx. So, let's see how we can relate theta to bending moment, m. When a beam deflects like this, its top fiber is compressed and the bottom fiber is stretched. To be more precise, it is not just the outer fibers that change length, but almost all the fibers in the beam change length. The top part of the beam goes under compression. Its fibers shorten. The amount of compression, however, varies from fiber to fiber. The outer fibers are compressed more than the inner ones. For example, fibers on plane A are compressed more than fibers on plane B. Similarly, the bottom part of the beam undergoes tension and its fibers stretch, but the outer fibers are stretched more than the inner ones. The closer we get to the inner core of the beam, the less compression or tension takes place. In fact, there is a surface inside the beam on which fibers do not change length. The fibers are neither compressed nor stretched. In effect, this surface separates the compression zone from the tension zone. We call it the neutral surface. In the two-dimensional view of the beam, we call it the neutral axis. So, when a beam bends, all its fibers change length, except for the fibers along the neutral axis. This fact helps us establish a simple mathematical relationship between the slope of the elastic curve and the geometry of the deformed beam. Let's see how. Consider a very thin slice of the beam. The width of the slice is denoted by dx. When the beam bends, this slice deforms like this. Let's refer to the arc length along the neutral axis of the slice as ds. This arc length can be assumed to be that of a circle having a radius of r. We refer to r as the radius of curvature. Then we can write angle d theta times r equals ds. By the way, d theta is the difference between theta 1 and theta 2, where theta 1 is the tangent angle of the left end of the slice, and theta 2 is the tangent angle at the right end of the slice. Let's rewrite this equation as d theta ds equals 1 over r. Also, let's make another simplification. Since ds is the unchanged length of the segment along the neutral axis, we can replace it with dx. So we can write d theta dx equals 1 over r, or d theta equals 1 over r dx. Integrating both sides of the equation, we get theta equals integral of 1 over r dx. Here we have theta expressed in terms of r, but we need to express theta in terms of m. Then the question is, what is r in terms of m? You probably know that the amount of deflection in a beam is directly proportional to the magnitude of the bending moment. The larger the moment, the larger the deflection. You should also know that the radius of curvature is inversely proportional to the magnitude of the moment. That is, as the moment gets larger and larger, the radius of curvature gets smaller and smaller. So it should come as no surprise that the product of the bending moment, m, and r remains constant in a beam segment. This constant value can be determined based on the geometry of the cross-section of the segment and the beam's material type. More specifically, m times r equals E times I, where E is the modulus of elasticity of the material, and I is the moment of inertia of the cross-section of the beam about the axis of bending. Now let's rearrange this equation. Let's rewrite it as 1 over r equals m over EI. This is the relationship between r and m. If we replace 1 over r with m over EI in this equation, we get theta equals integral of m over EI dx. And since v equals integral of theta dx, then we can write v equals double integral of m over EI d2x. This is the equation we were looking for, an equation that gives us deflection, v, for an arbitrary point in the beam. This equation turns into an algebraic one when we apply it to a beam problem. Let's see how. Suppose we have a cantilever beam subjected to a concentrated load of P at the free end. The beam's length is L. We would like to formulate an equation for the beam's elastic curve. Assume a uniform cross-section and a constant modulus of elasticity of the material for the beam. To come up with an equation for beam deflection, we first need to write an algebraic equation for the beam's bending moment, m. Then we shall perform a double integration on m over EI. The support reactions for the beam are a shear force of P and a bending moment of P times L, both at the fixed support. So the equation for the bending moment is mx equals px minus pl. If you are not sure how this is done, see lecture SA07. Now the double integration step. Here we need to integrate just m since both E and I are constant. Integrating px minus pl with respect to x, we get 1/2 of px squared minus plx plus c1. Integrating this expression again, we get 1 over 6 px cubed minus 1 over 2 plx squared plus c1x plus c2. Here, c1 and c2 are integration constants. They can be determined using the boundary conditions. Since there are two constants, we need two boundary conditions. They are slope of the elastic curve at x equals 0 is 0. Deflection at x equals 0 is 0. Here is the deflection equation. The slope equation, which can easily be obtained by taking the derivative of v with respect to x, is so at x equals 0, slope is 0. Therefore, c1 must be 0. Also, at x equals 0, deflection is 0. Therefore, c2 must be 0. Finally, the simplified deflection equation is v equals px squared over 6ei times x minus 3l. Before wrapping up this lecture, let's look at another example. Here is a simply supported beam subjected to a uniformly distributed load. Assume the beam has a constant EI. Formulate a deflection equation for the beam. The moment equation for the beam is mx equals 500x minus 50 times x squared. We know that deflection equals to the double integral of m over EI. Since the product EI is constant, we can write, or V equals 1 over EI times double integral of 500x minus 50x squared. Integrating 500x minus 50x squared twice, we get V equals 1 over EI times 250 over 3 times x cubed minus 25 over 6 times x to the power of 4 plus c1 times x plus c2. To determine the integration constants, we apply the boundary conditions. They are V at 0 is 0, no deflection at the left support. V at 10 is 0, no deflection at the right support. The first condition gives C2 equals 0. The second condition gives C1 equals negative 12,500 over 3. So here is the beam's deflection equation in its simplified form. This equation has multiple uses. We can use it to calculate deflection at a desired point in the beam. We can use it to determine the location of maximum deflection in the beam. Or we can use it to graph the beam's elastic curve.